By June 30th, 2026, Intel's market valuation reached a peak that defied recent internal struggles. Euphoria among investors reached a fever pitch. This chart shows recovery from August 2025 lows. A 650% rally drove the price to $142.35, reports concerning the 18A manufacturing process. These documents indicated that profitable yields, the percentage of usable chips per wafer, would not be achieved until late 2026 or even 2027. Investors had already bet on a perfect execution for the remainder of the year. This delay shattered those expectations, leaving the company's short-term liquidity in a precarious position. Behind the stock volatility, Intel is managing a high-stakes transition across two different business models simultaneously. The foundry division is currently a major drain on resources. In early 2026, the unit reported an operating loss of $2.4 billion, while bringing in only $174 million from external customers. At the same time, the company's core product division is steadily losing ground. AMD's EPYC server architecture is capturing data center market share right as the demand for AI processing reaches its peak. Supply constraints are adding further pressure. Large cloud providers are monopolizing capacity for AI chips, which forces secondary sectors to pay higher prices or accept hardware with reduced memory to stay within budget. This creates a moment of truth for the July 23rd earnings call. Intel must provide concrete evidence of 18A progress to convince the market it can stop this operational bleed. While the financial world watches the 2026 balance sheet, Intel's engineers have identified a bottleneck they cannot solve through traditional manufacturing alone. Modern AI chips rely on high-bandwidth memory, or HBM, to process massive datasets rapidly. This diagram shows why HBM is so difficult to scale. It requires a silicon interposer, the separate routing layer, and thousands of microscopic vertical connections called microbumps to link the stacked chips. Intel lacks the infrastructure to compete with the sheer volume of South Korean memory giants using this method, so they are developing an architecture that removes these physical requirements entirely. The plan is centered on a patent for cross-batch memory, or XBM. Instead of placing transistors on base silicon, XBM integrates them directly into the upper metal routing layers. This back-end-of-line integration eliminates the need for a separate silicon interposer, freeing space for much larger vertical connectors, which increases the total data the chip can move. This allows for memory-on-package designs, enabling high-performance memory to fit into much smaller, more efficient devices. Intel is betting that this architectural shift will eventually make current HBM production methods obsolete, bypassing the manufacturing advantages of their rivals. Despite the engineering potential, XBM offers no immediate solution to the financial crisis unfolding in 2026. Commercial adoption is likely years away. Intel has tied this technology to its post-2030 ZAM architecture, a long-term development project partnered with SoftBank. Even if the hardware performs as intended, the software ecosystem remains a massive barrier to entry. Today's AI applications are built specifically for the parallel memory interfaces used by Nvidia. This software compatibility acts as a powerful moat for the current industry leaders. XBM uses a serial interface called UCIe. Moving the industry to this standard would require developers to rewrite the foundational code governing how software accesses memory. This leaves Intel in a vulnerable position, replacing its core engine room while surviving a violent storm in the middle of the ocean. Success now depends on a single variable: whether Wall Street will continue to fund Intel's operations long enough for its 2030 vision to become a reality.